Hello and welcome back to Jameson's Ground School. I'm your host, Jameson. I will be talking about the Pitot Static system today. Some of our key elements are the pitot tube. We're going to talk about the static port. We're going to talk about alternate static source. We're also going to talk about several different instruments, the airspeed indicator, ASI for short. We're going to talk about vertical speed indicator, the VSI. And then we're going to talk about the altimeter as well. And then we're also going to talk about pitot heat, and then some errors that are associated with these instruments and some preventative measures as well towards the end. So jumping right in, we're going to talk about the pitot tube first. So here's an illustration of our pitot tube. What we have is a diagram of what happens inside the pitot tube. So we have ram air, which is basically the air that we, as we fly through the air, it's going to be that air that goes into our little pressure chamber here. Kind of on the outside of that, but still inside the structure here is the static chamber. And basically the difference between the two is going to be our measurement of our airspeed. Now we also have something on the backside here called the drain hole, which, as you would imagine, is what drains any excess precipitation that can be built up depending on where we're flying, if we're flying through precipitation or heavy rain, anything like that. And then these little red bars here are illustrating a heating element. Now what that does, basically, as we turn on the pitot heat inside the cockpit, that heats up the whole entire pitot tube. That can prevent any icing that we may encounter depending on our altitude, or if we're flying through precipitation or anything like that. That can prevent any ice buildup or accumulation on the pitot tube, as well as near the drain hole or the inlet here at the front. So moving to our diagram here, this is going to be an illustration of our airspeed indicator. So here's the ram air that's coming in and goes directly into the diaphragm. We also have a static air reading. Now this, like I said, is a pressure differential instrument that reads the difference between the two and gives us our indication here. So with this diagram, the diaphragm, as our air pressure increases, the diaphragm is going to expand, and then that's going to indicate a rise in our airspeed. And then conversely, as we lose airspeed, it's going to contract. Move this mechanical linkages here, as I wrote here with the little red arrows. It's going to spin the needles, and then on the inside lead toward the outside face and show the indications of that here on the face of the instrument. So that's kind of our airspeed indicator. Now that's directly related to information that we get from the pitot tube. So the pitot tube and the airspeed are our best friends. They work really well together, but we also get information from our static port. So I'm going to jump to the static port now and talk about that. Basically, that provides, the static port provides additional information of static pressure, typically from the outside of the aircraft, that reads our kind of ambient pressure from the outside and gives us indications of our static pressure. So the airspeed indicator is the only instrument that works off of all three. Now I'm going to get to these other instruments here, but I want to note too that both the vertical speed indicator and the altimeter work strictly from information from the static port and nothing from our pitot tube. So let's keep that in mind as we move forward. Now going to our vertical speed indicator, VSI for short, tells us where we're going in relation to up or down. So I have my mini Cirrus SR22 here. So as we increase feet per minute, it's going to move the needle higher in 500 degree instruments, 500 feet, 1,000, 1,500 feet per minute ascent. Or if we're going back down, descending here, it's going to show 500 feet per minute, 1,000 feet per minute, or anything in between as far as whether we are ascending or descending. Now back to our diagram here. Here's our vertical speed indicator. Here's the face of the instrument. Now we have direct static pressure reading that's going to come into the chamber here, but also we have something called a calibrated leak. So what the calibrated leak does is basically shows the pressure differential, and as the diaphragm collapses down on it itself, It moves the mechanical linkages, the rods and gears, and moves the needle on the face of the VSI. So both the diaphragm and the static pressure line, they receive information, and typically with the VSI there's a slight lag or delay from the difference between the static pressure and the calibrated leak. So it typically takes a couple seconds, 2 or 3 seconds, to kind of settle and give that accurate reading. And then some errors that come with that, we're going to get to at the end, but there are some errors that come with all 3 of these instruments that we'll talk about here shortly. But moving on to our next instrument is going to be the altimeter. Now, ALT for short is kind of the prefix to altitude. Now, this is a meter or a measurement of the altitude of what we are currently at. So we have 2 different arms here, a short little arm and then a longer arm. The short arm on our face here is going to be a measurement in thousands of feet. So this short arm is pointing to the number 2, 2,000 feet. Then we have the longer arm to the number 3, which is in hundreds of feet. It's going to be 300. So 2,000 plus 300 is going to equal 2,300 feet MSL. Now, looking at our diagram here, we have a stack of aneroid wafers. Wow, well, this is a little bit different than the other 2 instruments because these aneroid wafers are sealed and they are already set and adjusted to standard atmospheric pressure of 2,902. And what we can do that's different on this instrument is we have a manually adjustable barometric knob where we can set our pressure depending on our pressure altitude or density altitude, and then view that in what's called the Colesman window, which shows our current pressure altitude or density altitude. Now, as we ascend or descend, the pressure is going to expand or contract the stack of the wafers, move the mechanical linkages, and then give us the indications on the face of this instrument here. And then that's going to give us our reading of MSL, mean sea level, of where we are in the aircraft. So that's our altimeter. Now, kind of touch on the static port a little bit, but I'm going to move to the alternate static source. Now, this alternate static source is a secondary redundancy instrument, which basically we're able to flip a switch or a knob depending on the aircraft inside of the cockpit. Now, with this, if something were to freeze over due to icing or a bird strike or blockage of some type, we are able to use this as a secondary means to get a static pressure reading. Typically, the cabin pressure is what reads on this alternate static source, and that's kind of a secondary, like I said, or redundancy instrument to provide some reading if we were to have a failure of an instrument, a blockage, or icing, anything like that, just to give us some indications. Now, with that, there's going to be a little bit of a higher or kind of slightly erroneous reading, and I'm going to talk about that here in the errors section coming up shortly. But it looks like I have covered everything up to this point on my key elements that I wanted to talk about. So I'm going to ask the audience if there's any questions. I don't hear any, so I'm going to go ahead and pause right here and then pick up on the errors next. Hello and welcome back, aviators. This is Jameson for another episode of Jameson's Ground School. Today we're going to continue talking about errors in the Pitot Static system, some things that we might encounter, and then at the end we'll talk about some preventative measures that we can take to mitigate some of these things. So let's jump right into Pitot tube blockages. So I'm going to use this dry erase marker as a representation of our Pitot tube. So at the front, our inlet is going to receive that ram air pressure as we're flying through the air. But if that gets frozen over with ice, bird strike, any kind of bug, anything like that, that gets blocked. And also our drain hole at the backside gets blocked. We're not going to receive any ram air indications or any changes in static pressure. It's going to be blocked. So it's basically trapped on the inside of our Pitot tube. So the changes in pressure is just going to act like an altimeter. Okay. Now let's talk about if only our ram air is blocked. So here's just the cap on this side here for our ram air. That's blocked for ice or whatever reason, but our drain hole is open still. We're only going to receive a static pressure reading. So that's basically going to give us an airspeed indication reading of 0 when the ram air indications drop to 0. So it's going to steadily drop to 0 and then stay there. Now let's go over to static port blockages. So if our airspeed indicator, vertical speed indicator, and altimeter are all blocked because our static port is frozen over or clogged, something like that, airspeed indicator is going to get some readings because we still have the pitot tube, but the readings might be slightly inaccurate, so we need to watch out for that. A vertical speed indicator is going to produce a continuous 0 indication, not going to let us know if we're climbing or descending, it's just going to stay at 0. And then our altimeter is going to freeze or just stay stuck at the altitude at which it was frozen over at. So there's a quick summary of our errors on the pitot tube and the static port. Now, lastly, we have some preventative measures to go over that if we were to encounter something like this, we need to correct them and mitigate them as quick as we can, safely of course. So first thing is very important to cross-check all of our instruments and know our instrument indications, and constantly verifying and using these instruments as tools to know if something's a little bit out of the ordinary. So if the readings don't make sense or just a little bit more than unusual, just constantly keeping your eyebrows raised or something's just really weird, there's likely an issue. So trust yourself and verify with these instruments, and if something seems kind of weird, it's likely that something is a little bit weird. So also know our performance of our aircraft. So knowing our climb rate, descent, normal cruise, things like that, knowing our performance profile in the POH or AFM, knowing these numbers are going to give us better clues of what's normal and what's a little bit out of that kind of normal envelope and something that's a little bit weird. So if we suspect something like this, and if we get caught in heavy precipitation or flying IFR and don't really realize until it's pretty late that our pitot tube and static port is frozen over, we need to turn off autopilot if we're using autopilot, turn that off, hand fly, make sure our pitot tube is on, pitot heat is turned on to melt some of the ice if it's iced over. Exit the icing conditions as quick as we can. So climbing or descending, getting out of that icing condition area. And then if we need to declare an emergency. So safety is always the most important thing. So we need to make sure we're being safe. And if it becomes something very drastic, we don't really have a lot of time to play around or making sure that we trust our decisions. And if it gets to that point, don't be afraid to declare an emergency. So there's our summary of our errors for Pitot Static system today. We talked a little bit about the Pitot Static instruments, some of the errors, blockages, things like that, and preventative measures. So I'm going to go ahead and wrap it up here for today. So thank you for your time. I hope that I'll see you again on the next ground school lesson. And until next time, blue skies.